Let's solve two more integrals. These are a little more complicated than the ones we did before, but hey, that's what we're here for. The first one, we have x squared over x minus 6 dx. Now there's two different ways you could do this. The first one is rational division, and that's what I'm going to do. The second one, you could kind of use the addition subtraction method. We can look at that. We'll see how much board space we have. Okay. So the first one is this idea of rational division. So if you may not remember how to do this, and that's okay. What you do is you say, all right, x minus 6 goes into x squared. All right, so you say, all right, what does that mean? Division, what is this? All right, so the way you do rational division is you take a look at the leading term here, and you start from this term, and if you had more terms, we'd go from there, and I'll show you how you do that. You say, all right, what do I have to multiply by this to get that? So I have an x, and I need x squared, so I need to multiply by x. So by multiplying, now that I have this, I multiply it by every term over here, so I say x squared minus 6x. Now what I do is so you could think of this as being 0x plus 0. Now what I do is, just like in regular division, I take this and I actually subtract it from everything above. So x squared, if this is distributed, if that negative is distributed, I get a big old smudge apparently. I get negative x squared, but I get a positive 6x, right? Because I had a negative times a negative is a positive. So when I go down, I get 0 plus 6x plus 0. Now what I do is I say, okay, can this leading term be multiplied by something to get this? And the answer is, of course, yes, plus 6. So I can do 6, and I do the same thing. I say 6x minus 36. So then what I do is I subtract that. So this goes away. So I have 36. Now the problem is, this leading term, I can't multiply any standard or any positive powers of x by anything to get this. So this becomes my remainder. So because that's a remainder of 36, what I have is, this now becomes the integral of x plus 6 plus 36 over x minus 6 dx. So that's how you get that. With a little board space, I'm going to show you how you can get this with the plus minus method. But you have to be clever. That's the problem. Is to do this, you actually have to be clever. So what I could do is I could say, all right, well, what if I have an x squared up here, and I have an x minus 6 there? What would I have to multiply to get a difference of squares, right? What I want on here is something that factors into x minus 6. Specifically, I want something that factors into x minus 6, x plus 6, and then some leftover thing. So x minus 6 and x plus 6, well, that would be x squared minus 36. So that's x squared minus 36. But again, the 36 can't come from nowhere. So we have to add a 36 here. And then we have to split up the numerator and denominator to get x squared minus 36 over x minus 6 plus 36 over x minus 6 dx. And of course, when you factor that, it's going to be x minus 6, x plus 6. The x minus 6's will cancel, leaving an x plus 6 and your remainder term. So there's two ways to get there. But this way, you don't have to think ahead like you do on this. So it's really up to you. So once you're here, we can really separate that into x plus 6 dx, because these can be directly integrated, plus the integral of 36 over x minus 6 dx. So to do this one's a little more complicated. We're going to have to do a u substitution. We're going to have to say u equals x minus 6, du is dx. The direct integration here, we just add, we use the power rule. So by adding 1 to the power, so we get x squared, and then dividing by that power, so we get 1/2 x squared. We have a 6, that becomes 6x. And then we have this integral of 36 over u du. Well, if you recall, 1 over u du is a natural log, so that gets me 1/2 x squared plus 6x plus 36 natural log absolute value of u plus an arbitrary constant. Do not forget your arbitrary constant. So 1/2 x squared plus 6x plus 36 x minus 6 plus c. Never forget, you started in x's, you need to end in x's. Don't end in u's, end in x's, or whatever you started out with. Alright, the next one. Ugh. This one really wasn't that bad, it just took extra long because I did that piece. This one looks nastier, but it's probably not as bad as you think. But it is kind of ugly, right? You're like, oh gosh, how do I get this thing? So there are a couple of ways that this will work. What's kind of funny, you could do a double substitution. So if you pick u to be cosine, let's do it with a double substitution, and then see if we can do it without a double substitution. So the first one we'd say, all right, I'm going to let u be this cosine of x. But before that, actually, what I want to do is I'm going to say, I'm going to write it tangent that way. Now, what I find personally is that in a lot of integrands, writing tangent as sine over cosine yields a lot better results than just leaving it as tangent. It's not always true, but pretty commonly true. So when you have this, let's take u to be this cosine here. Let's say, all right, u is cosine of x. So du is negative sine of x dx. Okay, so I have a sine of x and a dx. I don't have a negative, so I'll put the negative over there. And anywhere I see a cosine, I can replace with a u. So now I have negative 21. So that's 21 and then the du. So the sine x and the dx go away. Sine x and dx go away and it's replaced with that negative du. This cosine is on bottom, so that's over u, natural log of u. Sorry, it's kind of ugly. Natural log of u over u du. Okay, that's great and all, but we're not really done because we kind of still have to think about this. Well, I know that the derivative of natural log of u is 1 over u du. So I can make an additional substitution where I say v is the natural log of u, dv is 1 over u du. So that'll take this integral and turn it into negative 21v dv. So then when I take the antiderivative of this, it's fairly straightforward. Negative 21 over 2 v squared plus c. But v is actually natural log to natural log of u squared plus c. But we didn't start in u's, we started in x's. So negative 21 over 2 natural log cosine of x squared plus c. That sure has a lot of parentheses, huh? Now, there is an additional way to do this. What you could do is you could say, all right, well, I'm going to take u to actually be that natural log of cosine. So by doing that, you have to be a little more clever, but it tends to work out actually better. So if I take u to be the natural log of cosine of x, what I can do is then use the chain rule. So when I take du, the derivative of the natural log of something is 1 over the something times the derivative of the something. So the derivative of cosine of x is negative sine of x dx. So then, if I pull that out, I get du equals, well, the negative du equals sine x over cosine x dx. Okay, why is this helpful? Well, if I look up here, I have sine x over cosine x, and I have a dx. So that's going to become my negative du. And natural log of cosine of x is my u here. So I have negative 21u du. That becomes negative 21 over 2 u squared plus c, which is negative 21 over 2 natural log cosine of x squared plus c. So you get the same answer, right? I just use brackets instead of triple parentheses. So what we find is that, you know, being clever, I guess, or using these techniques, specifically, you know, doing a little bit of crazy stuff or picking a little bit of odd substitutions can get us there. What we're about to embark upon are more complicated techniques, more tools in your kit. You're going to become an even better mathematician, right? A better evaluator of integrals, and this is going to help you out actually a lot in the long run.